In this video, we're mainly doing just basic review. This is really the first day of the course sort of content. We're going to review function notation, input, output, a little bit of interpreting of basic points. Probably the second video, I'll break it into two pieces. We'll get into review of revenue, cost, profit, and get started on interval notation. So let's jump straight into function notation. Remember that a function f of x, we may call it y equals f of x. We input the x value and the function will output a y equals f of x value. We need to be clear on the difference between f of 3 versus f of x equals 3, for example. So for example, if I give you a function f of x equals 2x plus 1, and I say find or solve f of 3, then in the separate problem I might say find or solve f of x equals 3. I want to be clear that these are different things. F of 3, if you compare that back to function notation, I might write right underneath it, f of x is y. Notice inside the parentheses is 3. Inside the parentheses is the x value. We're saying plug in x is 3 to the function and get out a y value, f of 3. So I'm going to go to the equation and I'm going to replace x with 3. So I have 2 times 3 plus 1. So f of 3 is 6 plus 1. F of 3 is 7. When we plug x equals 3 in, we get out a y value of 7. Alternatively, we may be asked to find or solve f of x equals 3. Again, comparing it back to f of x equals y. This time, the value inside the parentheses x is an unknown. They've been given y equals 3. So the y value is 3. The f of x is 3. We need to replace f of x with 3 in the equation. The equation was given as f of x equals 2x plus 1. We are replacing f of x with 3, replacing y with 3. So the whole left side of the equation here, the whole f of x becomes 3. 3 equals 2x plus 1. And now we need to solve this equation for x. So we subtract 1 on both sides, divide by 2 on both sides, and we get x equals 1. So if the y value is 3, then the x value is 1 on this function. Another example of function notation, if I gave a little sketch of a function f of x, so on this function, let's say it passes through the point negative 3, 0, negative 1, negative 5, and 1, 0, just as an example. And if I ask to find or solve f of x equals 0 on this function in the graph, again note f of x equals 0. If we compare it back, f of x equals y. This time we're saying y is 0. The f of x value is 0. The y value is 0. On this graph, that is this point here at 1 comma 0 and this point over here when negative 3 is the x. So there's two solutions, two places where f of x is 0. It occurs when x is negative 3, and it also occurs when x is 1. Separately, if I said find or solve f of negative 1, again, comparing that back to function notation general form, f of x is y. The x is negative 1. So on our graph, x is negative 1 at this point, negative 1 comma negative 5. F of negative 1 is negative 5. The y is negative 5 when the x is negative 1. All right, that's a quick review of function notation. Let's do a contextual problem, a real-world example. Let's say we have a function, C of t. C of t billion dollars is the value of the cumulative capital investment in the cell phone industry, where t is the number of years after 2000. So when we're given a problem like this, notice what that really means is that if, for example, t equals 0, that means the year 2000. You don't plug in t is 2000, you plug in 0 years after 2000. If t equals 1, that means the year 2001, 1 year since 2000. So in this case, the function is c of t, like f of x. The input is the t, so the input variable is t, which represents number of years since 2000. And the output is C of t, which is the cumulative capital investment, oh, it's okay, doggy, in cell phone industry. It asks us to write a sentence interpreting the real-world practical meaning of this function statement. C of 9 equals 285.1. So 9 is the 9 years since 2000. 285.1 is the capital investment amount, and it's in billions. So as a complete sentence, we could say, in 2009, the cumulative capital investment is $285.1 billion. If you want to write that out with all the zeros, it would be $285 billion, $100 million, if you like writing it that way instead. All right, and just the reverse, write a function notation statement for the statement. In 1990, the cumulative capital investment in the cell phone industry was 6.3 billion. So in 1990, that would be 10 years before 2000. So T would equal negative 10. The cumulative capital investment in the cell phone industry is 6.3 billion. So the C of T would be 6.3. Right? Because that would represent 6.3 billion. So as a statement, we write C of negative 10 equals 6.3. As a second example, this time they give us this function P of t, 85.2 times 0.924 raised to the t power. And they say t is the number of years after 1950. P of t is the population of a town in thousands. So it asked us to graph this function from 1950 up until 2020. So you could do that on a graphing calculator. Later, soon in the course, we're going to start doing this sort of thing on Excel. When you graph it from 1950 up to 2020, 1950 means t equals 0, 0 years since 1950. 2020 would be 70 years after 1950, so that's t equals 70. So when you graph it, you should be going from a low of t equals 0, that'd be right at the y-axis, up to a high of t equals 70. That will be years since 1950. Your p of t values will be here on the y-axis. The highest this function reaches is right here at 0, 85.2, and then it should go downward like this, decreasing concave up. It's a decreasing exponential function. So it should look generally like this when you graph it. All right, we're going to solve P of t equals 40. Notice this is saying the output is 40. We're going to solve for the value of t. You could do this graphically on your calculator. You might use a Calc intersect feature or the solver feature on Excel. I'm going to go ahead and solve it by hand using logarithms. So P of t equals 40. I replace the P of t with 40. Next, I'm going to divide both sides by 85.2. Now to get t out of the exponent, the only way to get something down out of the exponent is with logarithms. I'm going to use the natural log. I'm going to take the natural log of the whole left side and take the natural log of the whole right side. On the left side, I just have this number, natural log of 40 over 85.2. On the right side, we use the power rule. That will drop down the exponent, so t times natural log of the base. That's what the right side becomes. The left side is still just this number, natural log of 40 over 85.2. Now to solve for t, I divide both sides by natural log of 0.924. Ran out of room here, sorry. Take this up here. So the answer is natural log of 40 over 85.2, all divided by natural log of 0.924. That's what t equals exactly, but that's kind of useless to us if we want to answer this in terms of population and years. So I'm going to pull out the calculator and I'm going to type this mess in and get the t value approximately. All right, I popped that in the calculator and I'm getting a t of 9.57 approximately. So that represents 9.57 years after 1950. So in the middle of 1959, so it's 1959 and a half approximately. In the middle of 1959, the population of the town was 40,000 people, right? P of T is 40, representing 40,000 people, and the time it happened was 9.5 years after 1950, so middle of 1959. To find P of 30, this time again, comparing it back to P of T, they're telling us the T equals 30. So I need to go to my equation, 85.2, 0.924, and we're replacing T with 30. I'm going to just pop that right in the calculator in one step. I got about 7.95. I'm going to say I guess I'll take it way out, 7.954. So 30 is the number of years since 1950. So in 1980, 30 years after 1950. And the 7.954 is the population in thousands. So if we were rounding to the nearest person, this would say that the population is 7,954 people. That's pretty accurate. A little bit ridiculous to round it to the nearest person. We probably don't have that much accuracy with our model, but that is literally what it would mean.